somehow give an excellent introduction and the challenge for us looking forward, which is how to create new kinds of integrated systems. Moore's Law has been delivering a lot of value over the last 5 decades. The question is, how are we going to create this new kind of growth path? If you look forward, you say, well, there's a huge opportunity because our need for interconnectivity and our need to compute and communicate more is still increasing. So you'd say, well, if the way we've been doing it has ended, then this is clearly a huge opportunity. So, this panel is about new materials, and for sure you could see already from the previous talk, and we work on that too, is we try to find new phenomena that we could put into integrated systems. The problem becomes, how do we know what's good, and how do we do rapid prototyping where we get to the market and try many things at the same time? I can't just go and throw all sorts of new materials into TSMC's fab, right? So what we're doing is we said, all right, we had an opportunity to build sort of an adjacent fab that has maybe 4, 5, 6 mass levels that actually connects to a real foundry flow but doesn't change anything in the foundry. That allows us to integrate new kinds of materials like gallium nitride HEMTs, in-gas HEMTs, and GaN LEDs, which are our first targets. And here are the application areas that we're trying to address, power electronic systems. So what we're trying to do is we put models for the GaN HEMT right in the silicon design platform. And same thing for the in-gas and same thing for the GaN LED. So efficient communications, lighting displays, and photonics are the other targets. Now the problem is that, how do I get that rapid prototyping? There's 3 things changing at once. So what it allows us to do is to actually insert whichever platform we want into a standard foundry process and explore these technologies. 3.5 silicon epitaxy and thin film batteries are some of the targets we're trying to integrate. Thank you. We can then build prototype ICs using real design kits, get them into the marketplace to try to find new fundamental ICs that have great market value and be an aggregator of all those smaller markets, for a foundry. And then finally, as I was saying before, we can't use the same business models. You can think about this sort of smaller new enterprise as an innovative place that takes a lot smaller investment, but it can explore a lot of new market space. And when something really does reach a high volume, we can transfer that and license it to a foundry. So that's basically what we've been working on. So now I'll turn it over to our colleague.
So 2D materials, these are 2D, two-dimensional layered materials. They have ultra-thin body and pristine surfaces and can be very easily peeled off and can be transferred to any other substrate. These materials also offer a very wide range of properties, from metals to insulators, and the opportunity to create new materials simply by stacking different materials on top of each other, creating what are known as van der Waals solids. These materials have very unique properties which can be exploited for transformative applications. On the left-hand side, I show you a couple of applications such as transparent electrodes and which offer very high mechanical strength, transparency, and cost of manufacturing, simpler manufacturing leading to smart screens, for example. And graphene inductors, which offer again form factor advantages, higher performance and flexibility, leading to flexible wearable electronics. On the upper right-hand side, I have an application, a breakthrough application, which is using the MOS2, a molybdenum disulfide, another 2D material, a semiconductor, for making ultra-sensitive biosensors. And they can be low power, very low cost in terms of manufacturability, and can lead to a lot of applications from point-of-care applications to homeland security. And finally, we have shown, and other people around the world have been able to demonstrate, very high-performance 2D transistors made of monolayer, just a single atomic layer of molybdenum disulfide and tungsten diselenide that was shown in my group. And we can also combine these materials, to create ultra-thin, non-volatile memory, as well as 3-dimensional ICs, simply by stacking them and create the ultra-compact 3D ICs. And so these would enable, very high density, low power ICs of the future, and that would be necessary for supporting any big data kind of applications like Internet of Things and social media. So in summary, I believe 2D materials are the future of electronics, and they can potentially change the way we live, work, and play.
Hey, I'd like to talk to you today a little bit about the use of nanomaterials, especially in the application of enhancing heat transfer. I chose this application space because the dissipation of thermal energy becomes very, very important in terms of our ability to have electronics become reliable, as well as managing their thermal characteristics. And so in this example, the thing that I'm showing you is not so much the displacement of the current materials today, but an example of where we can go in the future with the use of carbon-based as well as polymer materials that will have ultra-high thermal conductivity for these applications. In addition to this, we also want to look at these materials for thermal energy storage. So in these applications, what I'm showing here is the use of polymer nanotubes that can actually have thermal conductivities that are as high as metals. And so this is a very exciting area because we can actually take these materials, and this is actually an example of a device that we used in DARPA where we actually had a silicon carbide device that was actually attached to a copper heatsink using polythiophene nanotubes that actually performed similarly to some other thermal interface materials that were being used. Why is this important? Because these materials have very, very good thermal conductivity, but also have very, very good mechanical compliance, which allows you to integrate chips onto surfaces with different CTE mismatches, which reduces the stresses and other detrimental effects that you might have. And so we're looking at using these in power electronic devices where you can shrink a wide bandgap power electronic devices down to very, very small scales, and also use these new interface materials in order to reduce both the form factor as well as the number of processing steps that you would actually have in these devices. In addition, we can use these coatings in order to tailor the surface energy to enhance two-phase heat transfer, which is also being shown here. This is also good for industrial systems, but as well as wearable electronics, where you would actually have the enhancement of evaporation from these surfaces. These kinds of planar structures can have thermal conductivities that are 5 times that of copper. And then the final one is showing you the use of these graphene nanoplatelets that can be used along with phase change materials. Again, thermal conductivities that are on the order of 50 watts per meter K, 2 orders of magnitude higher than the phase change material, yet with 90% of the heat carrying or heat storage capability of the PCM. And so these are very interesting areas where we can look at both the enhancing heat dissipation as well as energy storage capabilities.
My group has worked on the use of two-photon polymerization as a mechanism for 3D printing of devices for medical applications. The two-photon polymerization approach involves the use of the multi-photon absorption phenomenon for 3D printing at small length scales. We've been able to create structures with features as small as 200 nanometers using this approach. This approach can be used to process a variety of industrially and medically relevant materials, including polymers, ceramics, and polymer-ceramic hybrid materials. We've used this technique to process a variety of different structures for medical applications. On the top right, you can see a grid-like structure that we created out of a zirconium oxide hybrid material using two-photon polymerization and subsequently used for stem cell studies. We've also done studies involving bio-based photoinitiators. The structures you see on the left were created with a riboflavin-based photoinitiator that turns out to have better biocompatibility than glass. And we've used that for studies involving stem cells. We've also done some work on making small-scale medical devices, in particular small-scale hypodermic needles. So you see in the bottom center an image of a hollow microneedle that was created through two-photon polymerization out of a material that's used in hearing aid shells. So it's a very flexible material. And we've used both two-photon polymerization and microstereolithography to do 3D printing of essentially transdermal sensors. So devices that can be interfaced with the skin and interact with interstitial fluid. And we've created sensors for glucose, lactate, pH, potassium ion, glutamate, many different biologically relevant analytes through this approach. And so we believe that two-photon polymerization and allied approaches have the capability for making microstructured features for medical device applications and for other technologically relevant applications. And going forward, we see this as a useful approach for not only making tooling, but also through holography and other approaches for doing commercial scale fabrication of small-scale devices.
In my laboratory in Houston, we use theory, mathematical models, and computations to explore materials and nanostructures for useful applications. And this area has its own technology, as highlighted recently by the Materials Genome Initiative. And MGI paradigm comprises 3 different levels, as this diagram illustrates. At the basis, there are computing methods of high precision, which are also very expensive, and they can treat only a handful, a dozen of samples of materials, selected materials. And this creates what we call training set. Then in the center of this all is this model, well-designed model, which captures important property as a function of simple descriptors. And this model can be, in different ways, trained by fitting it to match precisely the training set. After that, this central model becomes a powerful, like magnifying glass, as shown here, which allows one to generate rapidly very large database of properties for thousands of materials and compositions, and then one can pick and choose what is useful, what is best for his application or his goal. Recently, we applied this approach to a couple of examples from this new class of 2-dimensional materials. And in one case, we discovered that, for example, alloys of carbon and boron nitrogen can be designed in such a way that they have energy band gaps desirable for microelectronics applications. In another example, we discovered that in the family of metal dichalcogenides, 2-dimensional again, there are certain compositions which have very high catalytic activities. So along these lines, we anticipate developments leading to disruptive technologies. Future.